Hello and welcome to the module 4.3. In this, we will learn mainly about the sampling and intervals. These are also very important concepts, how you do the sampling, how you try to identify the intervals. So that help you in the downstream analysis. So this is a great starting point. If you have already done the descriptive statistics, if you have already know the probability essentials and all those things, then sampling and intervals can help you to add little bit more information about the data that you are going to explore in your downstream analysis. So are you guys ready? Let's get started with the sampling and intervals. So in sampling and confidence interval, the main concept is the sampling method, central limit theorem, standard errors, and building and interpreting the confidence interval for the means and for the proportions. These are the main things that you will learn in this particular module. Specifically, learning objective will be defined. So we have to choose the appropriate sampling method. So there are n number of sampling method that you can try, but you need to select the appropriate method in such a way so that you are not using anything biased towards one particular samples or towards one particular group. So here the sampling method makes sure, the best sampling method makes sure that you have a less number of bias and you are representing the all groups in the same way and in the same manner. Then we'll explain the CLTs and the standard errors mainly. Then we'll discuss about how to compute the confidence interval from the mean and proportions in the data. And last, determine sample size for the target margin. So first is the sampling method. Sampling method is simple SRS. It will go in the numbers and name. This is a simple random sampling, which is unbiased but potentially having high variance. Okay. So if you have the 1,000 instances belonging to two different groups, okay, so the when you are picking some of the instances from 1,000, let's say you are picking random 100, random 200, random 500, so you need to make sure at that particular time when you are doing the random sampling, there should not be a bias towards a particular group, otherwise your downstream analysis will highly be affected. So that is very important. Should be stratified if you are doing the stratification. So let's say if I will give you the example of 1,000 instances, you have some group 1 that belongs to like 300 instances, group 2 belong to 700 instances. This is in total. What if you will pick 100 and those all 100 are coming from group 1, or one group is highly represented in those samples? So whenever you will do any kind of test, whenever you make any kind of hypothesis, any kind of analysis, that will be super and highly biased to that particular group. So at this point, at this particular point, stratification provide you the important feature. Like a stratification is a good way, so that when you are picking the random samples, you are telling the algorithm to pick in the same proportion the instances from the group that are in the original dataset. So you are reducing the variance by grouping the similar units. Cluster is another efficient method in which you are doing the cost efficient for the geographically dispersed populations. So clustering can be another approach. And then the systematic. In the systematic, it's a easy implementation with the potential periodicity and the issues. So again, the sampling method are dependent upon the kind of questions that you are asking, whether you're going for the random sampling. Random sampling is always good because in this, like, you are not particularly biased, but the problem is it has a high variance. In stratified, you have a limited amount of variance. Clustering, you can focus on the geographical dispersed population based on the similarity and differences they have. And the systematic, you can systematic has an easy implementation, but it can have some other kind of issues. So these are the in short four kind of sampling method that you can try. What I would recommend you, whenever you have some kind of data sets, whenever you have some number of instances, try all four and see how the variance vary across data sets, how the groups vary across the different across the different sampling method, and how the biasness vary across the different groups in the across different sampling method that you are trying. Now you learn the concept about the bias, variance, and sampling error. These are very important when you are doing some kind of sampling. So relationship between the key statistic concepts in sampling methodology, here is a key: population versus sample. So here, population contain all possible data points. Let's say you are collecting a data very simple of any general population, and you are trying to identify that in that particular population in the location, how many people are interested in one kind of event, how many people are interested in other kind of event. It is not possible for you to go and collect the sample for the entire population. So that's how you do sampling. You pick a few samples from the population, you take the observation from those selected instances, selected individuals, and then you hyperpole it to the entire population. Okay, so this is the different. Samples population is the all possible data points, while sample are the smaller subset. Sampling introduce the variability in the estimates. Okay, whatever estimates you will make, there will be highly variation depending upon the kind of sample sets you have selected. Let's say if you are making the opinion in a particular constituency about the people who are preferring one political party than the other political party, but what if you are doing the sampling in a location in which that particular location or the people you have selected from that location are already biased towards one particular party, or so your sampling set is not balanced, your sampling set is already biased, so the results you will make, the interpretation you will make will be biased at the end. So this is very very important concept. You need to learn about the population and sample, how carefully should select the sample set to make any inferences or make any decision for the entire population. Sampling is the difference between the sample statistics and the population parameters. So this is sampling. It can be influenced by both bias and the variance in the estimates. So bias can be introduced at the time of selection of the subset from the population, and the variance is when you have the bias, you will see the variance, you will see the variability in the estimation or in the final predictions. So you need to understand the difference between the sample statistics and the population parameters to reduce the bias, to reduce the variance in the estimates and in the predictions. Bias is simply a systematic error that you do cause the that cause the estimates to consistently miss the true parameter value. When you are consistently picking the individuals from a particular group, from one group, and you are using in your analysis, so you will consistently miss the other parameter, you will consistently miss the other group to make some kind of inferences. So this is systematic bias, and that you generally do at the time of sample selection. Then it comes to the variance, which is spread of the sample statistics across repeated samples, reflecting the estimation of uncertainty. So variance is a very good parameter when you are doing random sampling multiple times. You are computing and checking the estimation uncertainty across the sample subsets that you have selected, and that variance give you a flexibility, that variance give you a confidence in your estimation, in your predictions. Here the key insights is bias variance trade-off is fundamental in statistics. Techniques that reduce the variance, any technique, be it sampling techniques, be it computational technique, which will reduce the variance often increase the bias sometimes, and increase and vice versa. So you should have a higher variance. Make sure you are capturing the enough sample set, you are capturing the enough diversity in the data, so that you are not biased towards any kind of predictions. After this, it's a central limit theorem. It's also very very important to understand and learn for the sampling strategy or for. So for large n sampling distribution, the sample mean is generally regardless of the population shape, it's normal sample mean. So that means if you are taking this, considering the central limit theorem, you will get the sample mean that will, regardless of the population shape, regardless of the population size, that reflect the complete population mean, and that you can compute using the, that you can get by the sample mean. So CLT, central limit theorem, actually explain why normal distribution are so prevalent in the nature. As we aggregate many independent factors, their combined effect tend towards the normality, making it a foundation for the confidence interval and the hypothesis testing. So normal distribution generally centered around the mean, and they actually help us to identify the confidence intervals, and that is very very important parameter to compute the to do the hypothesis testing, to identify the outliers and all those things. So in this, in the normal distribution, in this kind of distribution, it is very very important to identify the standard error for the means, whatever means you are computing. If this is a perfect normal distribution, the mean you are getting, there is a less chances of getting the standard error. But there is not a perfect distribution, then the chances of getting the standard error is high. The outliers, that the mean can be super sensitive to the outliers and all. So you need to measure the standard errors. So measure the standard deviation from the sampling, overall sampling distribution. You can use sigma when the population standard deviation is known. Otherwise use s when you have the sample standard deviation. Either you will have a population standard deviation or you will have a sample standard deviation. And by using the sample standard deviation or population standard deviation, by doing the square root of n number of instances, you can get the standard error, and that is standard error you can use for the mean. So whenever you are reporting anything, you are reporting the mean value. At the time of reporting the mean value, you can report this standard error also, like how much it can be up and down based on the data that you have provided. Then there is a very important is a standard error of the proportions. In the proportion also you can compute this standard error. So measure the variability across sample population. So there is one sample population, you measure the variability, then you will measure for the another sample population. For planning, use p is equal to zero point 0.5 when you are unsure about the expected proportions. So you can use the expected proportion as a zero point 0.5, and if you don't know the information about the expected proportions, you can use this formula of the proportion 1 minus p expected proportion divided by total number of n, and you can take the square root. You will get the standard error of proportions. Now you have the standard error for means also, you have a standard error for the proportion also, and now you can compute the margin of error. So margin of error can be computed by using this particular formula. Margin of error, MOE. Z you use for the large samples, SE or T used for the small samples, multiplies by SE, that is the standard error that we have computed for the means. So by using this formula, by multiplying the Z confidence interval critical values with the standard error, uh, with for the sample for the smaller samples, and for the larger samples you get the confidence interval, and by combining these three you get the margin of the error. Now these three things are very very important. As sample size n increases, standard error always decreases, because standard error, if you are taking only like couple of instances, 5 10 instances, there are high chances that you will do the standard error will be very very high. That's why we say that when you select a population, when you select a sample set to reflect your effect or predictions on the population, what is your sample size? If your sample size is low, we will expect that you will have a chances of error will be very very high. If your sample size is very very high, chances of error will be low, because you are covering the enough amount of individuals from the certain population to make some kind of decisions. Now you go for the confidence interval for the mean. So now confidence interval for the known populations and confidence interval for the unknown population. These are the two things here. So let's define this. I'm not going into the formula. Z is the critical value from the standard normal distribution. We get the Z value. It the confidence interval from the population help you to identify what is the range, what is the total range in which with the 95% of the confidence the data is overall spread. It rarely used in the practice as a population, which is population standard error is usually unknown. But when we go for the confidence interval for the unknown population, so in the unknown population, when you don't know the critical value, the t distribution is always n minus 1, which is a degree of freedom for you. So this is more commonly used formula in the practice, because for generally for the populations, unknown populations, we use this kind of confidence interval here. Then you assume the sample size. Using the confidence interval, you can compute the sample size. Once you have the information about the confidence interval, you can go for the sample size, small samples. That population should approximately normal. As n increases, if you increase the number of samples, the t distribution approaches to the normal kind of distribution. So check if your confidence interval is valid, and based on the those confidence interval, you can select the population size if the population is normal. Okay, the margin of error for you, the margin of error is the second part of the formula. You can use the margin of error also. Wider intervals can help you to identify with the more confidence, but with the less precision. So ultimately you can use this confidence interval to make some assumption and to select your sample size. So we did the confidence interval for the mean. Now the same thing you will do the confidence interval for the proportions. So you get the standard confidence interval for the proportion. This is the standard formula you get. So, and then you get rule of thumb for the validity. When you use these conditions are satisfied, then the sampling distribution of p is approximately normal, making the standard CI formula very very reliable if you're using this. Or you can use the standard confidence interval for the proportions. Then there are some kind of scores like Wilson score interval for specifically for the smaller samples. If you are getting very smaller number of samples, and if you like to compute the confidence interval, then use these kind of scores rather than this standard confidence interval or rule of thumb variability. Then you will go for the sample size planning. Once you have computed the confidence interval, using the confidence interval, either using the variance or using the proportions, when you decided that what sample size you would like to go, you can plan it. So for mean, you can go n should be greater than this formula, which is z is a critical value and sigma is the standard deviation and moe is the margin of error. So this n, which you will represent here by considering all these three information from the population, will provide you enough information, will be free from the lot of error in the estimates or prediction you will make. So that can be considered as a good sample size to start your analysis after doing all those calculation. If you are computing the n from the proportions, a number of the samples that should be considered in the study, then you can use this formula in which p is the estimated proportion. You have the estimated proportion, you are using the margin of error, then you are dividing the estimated proportion from 1, get multiplying by the estimated proportion. If the proportion is unknown, you can use the p value is 0.05. So it depends whether you are using the mean or you are using the proportion to compute the samples, but ultimate purpose is select the sample set that you can use to make the good predictions with less proportion of the error, less proportion of the expected errors in the end. Consider practical constraints like budget, time, population size, and required precision. A lot of things are there. Let's say if you are getting from the proportion or from the mean, if you're getting like 1,000 samples are required to make some inference or some make some good predictions, reliable predictions on certain population, but if you're not getting the 1,000 samples for that particular study, then you need to come up, revise your analysis, come up with the lower number of sample size, and decide if you will consider a little lower number of sample size, what you need to you need to taking care of at the time of making prediction, what kind of errors you can expect in those kind of sample sets. So those decisions depends on a lot of other things, but you select, in short, you select the samples using these parameters which we have discussed, either the proportions or using the means. Now example, confidence interval for the mean. How we will do the confidence interval for the mean? Identify first the sample statistics. When you have the sample mean of, let's say, 52.3, sample standard deviation is, let's say, 10.1, sample size is 64, we want to construct a 95% of confidence interval for the population mean. How will do that? Now for the population means, you can do calculate standard error and find the critical value. So calculate the standard error first. Now you have the standard deviation, you have the sample population, sample size. So from the standard deviation and from the sample size, 10.1 divided by 8, 1.26. So now 1.26 is your standard error. Now for 95% of the confidence interval, you can define df, which is n minus 1, which can be 63, and your t critical value can be 1.99. And that's how from standard error, from confidence, from for 95% of confidence, you will get the degree of freedom. Using the degree of freedom and critical values and the standard error, you can compute the you can compute the complete standard error. Now you can compute the confidence interval using the x, using the t which you have computed critical value, using the standard deviation that we have computed, and the total sum size. You will get the confidence interval for the formula. Now subtracting our values from the confidence interval, once you will get the confidence interval, you can add and subtract the information that we got, like the critical value. You can add the standard error. So that's how you first add those things and then subtract those things, and you will get the confidence interval in the range of like 49 to 54 for this particular data sets. Now your mean is 52.3, your confidence interval is 49.79 and 54.81. So this is a lower limit, this is a higher limit, and more than this it can be outlier because it is going beyond your confidence interval. How you will interpret these results? We are 95% of the confidence that true proportion of the means will vary, always vary for the entire population between 49 to 54. Actual mean is 52. So now you have a particular range. If something is going out, that is the error in your predictions, errors in your calculations. This is very simple to calculate. Now, if you'll use CI for the proportions, what you will do, you will first compute the proportions. Let's say given 120 successes out of 400 trials. So your proportion is 0.30. Once you got the proportion, then you will determine the critical value. Critical value will determine which is 95% of the confidence interval. Let's say that is 1.96, standard normal critical value. Then you will compute standard error of proportion. Standard error will be computed by this formula. You have some proportion, you will use 1 minus that proportion divided by n. By doing this formula, let's say you are getting the standard error of 0.002. Now you will compute, after standard error, you will compute margin of error. Now margin of error will be from the z, which you already computed, z minus z multiplies by the standard error. So this is marginal error 0.004. Now you will use marginal error, standard error, and your probabilities, everything. So you will get the confidence interval. So 95% of confidence interval, you will get the proportions, the success that you are getting 0.30 plus and minus of 0.04, which is a marginal error. So from here you will get 0.25 and 0.34. So that means we are confident by using this data. 90% of the confidence says that the true population proportion is always between 25% to 34%. It will not go beyond that. If the value proportion is going beyond more than 34 or less than 25, that means those kind of errors should be considered. Those are your marginal errors. So you learn everything, like how you will compute the confidence interval for the proportion, how you will compute confidence interval for the mean, how you will compute the sample size. We discussed about the confidence interval for the proportions, means, how they important, why they are important, why you should consider those informations. And once you will get those confidence interval, how confident you are presenting your data based on the sample sets that you have utilized. Remember, confidence interval is a procedure with the coverage rate, not for the probability statement. Wider the confidence interval, higher the confidence level. Larger sample size produces a narrower confidence interval. If you are getting the larger sample size, you will definitely get the narrower. But if you will use the smaller sample size, your confidence interval will be very very high, and you will have a very high chance of the error also. Report both point estimate and the confidence interval for the communicate uncertainty in the result. If you are only presenting the confidence interval, it might not represent the uncertainties. But if you will report both estimates as well as the confidence interval, that will actually present the all the uncertainty that might be having in your model, in your results. So anyone who is using your model, anyone who is using your result, anyone who is making some decisions based on your results, they will have this idea of like what is the range and what are the chances to get some kind of errors apart from this. So here you can quickly check which statement about 95% of confidence interval is correct. And the answer for you guys is, if we were to repeat the sampling process many times, about 95% of the computed intervals would contain the true population parameters, and there will be a 5% of the chance of. So this is all about the sampling and confidence interval. Now you understand why this confidence interval is important, how you can compute them from the mean, from the variance, and those are the very very small things you should keep learning and you should adapt in your analysis. And now I will see you in the module 4, in which we'll discuss about the hypothesis testing.